Okay, so I'm going to talk about Ricci curvature and limit spaces. So the motivation for all these talks will be the following. So I'll explain the term of the question, but assume that MIN GI is a sequence of Riemannian manifolds with Ricci curvature bounded from below. So Ricci of the metric GI is greater than, let's say, minus n minus 1 GI, and that, I'd say probably tomorrow what that means. But let's take that for granted now, that this sequence of Riemannian manifold converges to some limit space. So that's Gromov-Hausdorff topology, but we'll come to that at some point. What can be said about this limit metric space? So, this is, well, so basically this should be thought as a reader's guide to all the business that have been going on in the last maybe 20 years now in this topic, including the world of Cheeger and Colding, of Tian, more recently of Neighbor and stuff like that. So we won't go to all this fancy new stuff. We will focus at the end of the lecture on maybe one of the first results in that direction, which is the almost splitting theorem by Cheeger and Colding. Let me give an outline of what I'll do. So first today is Riemannian geometry. It's a survival kit. Tomorrow I'll talk about Gromov-Hausdorff convergence. And examples of what can go wrong when you take Gromov-Hausdorff limits. Then I'll set up the main tools of the field, which is Ricci curvature comparison theorems. And the main applications. And probably in the last two lectures, so I will talk about Cheeger, Colding, almost splitting. Okay, so let's move on to the first part. So we'll work with Riemannian manifold, MMG. So recall that Mn is a smooth manifold and that G is a smoothly varying inner product on each of the tangent spaces. I will often denote G by like the usual inner product in Rn for convenience, and the norm likely. So what can we do with a Riemannian metric? First, we can differentiate vector fields and tensors. So there is one usual way to do that. It's the Levi-Civita connection. So basically, it's just tailored to be able to do calculus as in Euclidean space on a Riemannian manifold. So it satisfies the good properties that you would expect from some kind of derivative. So, okay. So that's a theorem. So there exists some operator D. So gamma of Tm will be sections of the tangent bundles, so vector fields. To same stuff. So which satisfy x maps to dxy is C infinity linear to. So in other words, when you differentiate, it depends only on the direction of x. Second property is that y maps to dxy is a derivation. So it's R linear, and when you multiply your vector field by a function, it satisfies Leibniz rule, and it satisfies some commutation relation, namely that when you take the difference, the anti-symmetric part, it gives back the Lie bracket. So this is torsion-free property. And next, when you differentiate an inner product, well, Leibniz rule applies. Okay, so I won't do the full details of that, but at least one case will be quite important for the object we will consider, is that one can extend D to tensor bundles. And once again, the only thing that you want is that Leibniz rule holds. And that's about it. So, for instance, if alpha is a one form and x, y are vector fields, so I can take alpha of y, so that will be a smooth function on my manifold, and I want to differentiate that. So I take x dot of that, and I want Leibniz rule to hold. So this I don't know how to compute, but I want this relation to hold, and this. Oh, I should stick to D. So I choose D and not nabla for some reason. I should stick to it. So, and this is the definition of dx alpha for one form. Okay. So I had something else to say about this. Just there is another way to differentiate tensors and vector fields, which will be of some use in the sequel, and the interplay between that and the connection is actually a powerful tool. So we did the covariant derivative. Before you learn about connections and Riemannian geometry, there's also the Lie derivative. And well, when after learning about Riemannian geometry, I started to forget about Lie derivative, but it's actually a powerful tool in computation. And it also yields pretty nice geometric interpretations of things. So maybe just a quick recap. So we'll follow the same road. So we'll define it on vector fields first, and we'll extend it on one forms and other tensors using this idea. So, and basically, x, y are vector fields. Lx, y is just the Lie bracket between x and y. And if alpha is a one form, for instance, so I want that x dot alpha of y is equal to Lx alpha of y plus alpha of Lxy. So that's a really formal definition. Maybe that's not the good one. Where? Here. Yes, sure. So yeah, that's really formal. It probably seems useless like that. But it has a really nice geometric interpretation when you define it on various tensors. It's the following one. So another definition. Will be the following. So you take phi t to be the flow of x. So you take t to be some tensor. Let's say a metric, for instance. That's really interesting for a metric or for one form. And then Lx of t is the derivative at time 0 of the pullback of t. So that actually tells you how the tensor moves when you follow the flow lines of x. Maybe an application of this idea before moving on to the other objects that will be of interest. Okay, it is the following. So, definition. So a vector field on, so a vector field x on a manifold Mg is a Killing field if the Lie derivative of the metric in the direction of x is equal to 0. So what does it tell you actually? So when you follow the flow of x and you act on the metric, you always get the same metric. So, so there's a proposition so if you have a Killing field, then if you look at what this field does on the metric when you move along, so phi t star of g, it will always be equal to g. So the flow acts by isometries. So that's an equivalence. So I'm considering complete vector fields on complete Riemannian manifolds. And I'll say what complete is shortly. So yeah, this way to this way is really easy. It's just applying this part of the definition. In the other sense, it's not much harder. Okay, so, well, for now it was just calculus, basically. So we'll get back to calculus because, so yeah, the topic of my lecture is geometric analysis, so there's some calculus involved. But maybe let's do a little bit of geometry first. So it was differentiating tensors. So now let's talk about the distance on a Riemannian manifold. So geodesics. And we'll also talk about normal coordinates, which are a powerful tool for understanding and for computations. Okay, so once you have a Riemannian metric and you have a curve C in your Riemannian manifold, you can define what is the length of the curve. So the length of the curve will just be the integral from A to B of so the square root of G of C dot, well, should put variables, C dot of t, dt. And we defined, so if x, y are points in M, so the Riemannian distance dg between x and y is equal to the infimum over all curves C from x to y. So yeah, maybe wiggle of the length of these curves. So this only depends on the geometric image of the curve. This is invariant by change of parametrization. So from an analytic point of view, it's not a really good functional. So when you want to find like shortest curves and stuff like that, this is not the stuff you minimize, you take energy. But then when you take energy, you get a nice equation. Definition. Take the Euler-Lagrange energy, not the Euler-Lagrange equation, not of this, but of the kinetic energy of the curve. And the two are related. They have up to reparametrization, more or less the same minimizers. So definition, a curve C is a geodesic if it satisfies the following. So C dot is a vector field along the curve C, and you can differentiate it using the Levi-Civita connection in the direction of C dot. So that's well defined. That requires a little bit of work, but it's not too bad. And you ask this to hold. So what are the properties of geodesics? So for every, so let's say tangent vector V in some tangent space at M there exists a geodesic C from, well, let's say maybe some open interval, small, around 0 to M, such that, so it starts at P with the direction V. So C of 0 equal P, and C dot of 0 is equal to V. Okay. And there's a really nice, so that's basically like the standard existence results for ODEs. There's a really nice theorem by Hopf and Reno. Which says the following. So, well, let me phrase it this way. So, geodesics exists for all T in R. So this is equivalent to, so M together with the Riemannian distance is a complete metric space. So, and now we will always assume that our manifolds are complete. Another consequence of these two equivalent hypotheses is that any two points can be joined by a minimizing geodesic. So it follows from this Euler-Lagrange equation that on small time intervals, geodesic will be length minimizing, but they need not be globally length minimizing. For instance, okay, yeah, maybe start something. So let's consider an example of an open manifold that Silva mentioned, of an open surface actually. So consider the round cylinder. In R3, for instance. So if you unfold it, you get, if you cut it in the middle and you unfold it, you will get a nice flat sheet of paper. And so the geodesics are the same as the geodesics in the plane. So they're just straight lines, but which can roll around this example. So this is a geodesic. I'm not sure if this is the perfect drawing. And it's minimizing at the beginning, but once it reaches, is it this point or this point? This point, you can take a shortcut by going the other way. So color choke. So if you want to go from here to here, it will be shorter to do that trip than to pass through this. So geodesic need not be globally minimizing, but they're always locally minimizing on small intervals. There can be geodesics which are always minimizing. For instance, if you take this line here, it's always minimizing. Okay, so what can we do with geodesic? We can define the following. So the exponential map. So, okay. So what is the exponential map? It's just the following map. You stand at a point in your manifold. It's a function which is defined on the tangent space. So at this point, you choose a direction, and then you walk in this direction for the length of the vector, and you look at where you stand. So more formally, so it's a map which goes from TPM to M, and which does the following. So to a vector V in the tangent space, you associate what I will call CV of 1, where CV is the unique, by standard ODE argument, geodesic, such that so V, so yeah, C of 0 is equal to P, CV of 0 is equal to P, and C dot V of 0 is equal to V. Okay. So this is the first time where completeness is actually important, because this will allow this map to be defined on the whole tangent space and not just on some neighborhood of the origin. Okay. So what's nice with this map, and I guess what made the appeal of Riemannian geometry at its beginning, is that we have a preferred system of coordinates here. So this gives some special system of coordinates. And we will see actually that it's pretty convenient for computations. So, well, I guess if I want it to be a chart, I need it the other way. So this map is called exp at the point P. So this gives the preferred system of coordinate. But if I want good coordinate, I need that to be smooth and a diffeomorphism. So, well, locally around the origin there's no problem, because by definition the differential of this map is the identity, so you can use the inverse function theorem. But you would like this coordinate patch to be as big as you want, and that's why we define the injectivity domain. Okay. So denote that by injectivity domain of the point P, and this will be the following. So this is the set of vectors V in the tangent space, such that there exists epsilon positive with C. So you start with a velocity which is slightly bigger than V. And you want that when you follow for this amount of time this direction, you stay a minimizing geodesic. We'll do example afterward. Is minimizing bad idea. Here. geodesic from 0, 1 to n. Okay, so, well, maybe let's unfold this cylinder and look at what it looks like in that simple example. So this is my point P. So let's assume that, so this is a cylinder of radius 1, so the length of this particular curve will be pi, and if you do the whole, if you get all around, you will get 2 pi. So if I cut that here and unfold it, then I will get the following. So 0. And as this example suggests, as soon as I hit this part of the cylinder, I stop to be minimizing. So the injectivity domain here will be some strip, some open strip around, let's say, an horizontal axis, if you think of the tangent space this way, and of width pi. So this, or maybe I should use the 2 blackboards, it's the same price, yeah. So is that here? Okay. So, okay, why is that important? Well, facts. So actually this is the biggest part of the tangent space on which this exponential map is a good coordinate chart. So fact on, so the injectivity domain of P. So X P is a diffeomorphism onto its image. So that's fact 1. Let's say. And fact 2. So if you look at the, okay, maybe let's try to do another simple example. So look at the sphere. So let's think of the tangent space here. Maybe I'll draw it in another color. So geodesics on the spheres are great circles. So geodesic from P goes this way, and then they come back, but they stop to be minimizing after that point because I could have gone the other way around on the great circle. So here, so when I take the vector which goes all to this way, I've already left the injectivity domain. So the injectivity domain here will look, oh, should respect my color code, like that. So this is injectivity domain of P. And the radius of that circle is pi. Oh, yeah. Well, maybe that was implicit here. But this is open. That's why the epsilon in the definition, to make it open. And this is also star-shaped with respect to the origin, which is actually a really geometric fact about geodesic, which tells you that if you're minimizing, then on each subsegment you have to be minimizing. So yeah, so that's a nice open star-shaped domain. And the question is, so in these two examples, here we missed a line. So the domain here that is covered by this coordinate chart in the cylinder was everything but the top axis here. Here it's everything but the south pole. And it's a general fact that this chart doesn't miss much. So let's give a name to this set of bad points. And actually most of the subject that most of the difficulties that we will deal with in the sequel is just these bad points. So we'll define the cut locus of P to be the points in M which are not in this good coordinate chart. So here is the south pole, and there it's the top line. Then this set of cut points has measure 0. So I haven't defined yet what is the natural measure on the Riemannian manifolds. But being of measure 0 is a property which is invariant under diffeomorphism, so here that makes sense. So yeah, we miss few points, and actually we can tell exactly what's going on. So I'm in my tension space, I have my origin. So the injectivity domain will be some star-shaped domain. Maybe it has, is it still star-shaped? It's not that easy to draw a random star-shaped domain. Yeah, I think I failed actually. So all this guy will be a smooth coordinate chart. So xp is smooth, here is a differo. And all this is mapped on the cut locus of P. So yeah, already that tells something about manifolds in general, is that so this is diffeomorphic to a ball. And so every manifold, you can see it as a ball with some gluing made at the boundary, given by the exponential restricted to the boundary of this set. So, well, that's not really restrictive, because if it's valid for every manifold, it doesn't give you much. But still. Okay. So now, what does the metric look like in these coordinates? That's actually really pretty nice. Okay, do I need another fact? Maybe let's call that fact 3. So I have the metric on M. I have this coordinate chart. I can look at what the metric looks like in this coordinate chart. So how do I do that? I take the pullback of the metric on M through this exponential map. And I get the following stuff. The pullback of G here is of the following form. dr squared plus some metric HR. And HR, so this is a one parameter family of metrics on Sn minus 1. So tells you that if you look at polar coordinates here in TPM and at this radial direction, then you actually get a really nice splitting of the metric in these two parts. So this has a geometric interpretation, which is not surprising. It's that, so by definition, this like Euclidean sphere in the tension bundle of some radius, let's say big R, is mapped to the metric sphere of radius R inside the manifold. And the geometric thing between this fact is that when you take a point from the origin and you travel in straight line to the sphere along this geodesic, then you will meet the sphere orthogonally. That's called Gauss lemma sometimes. Okay. So and actually this is, we will see some case where this representation is actually really useful. So examples of how the metric look like in these coordinates. Okay, so remember the classification of by Sylvain of manifolds between small, medium-sized, and big. So we will have the same class of example, more or less. So maybe I'll start with the medium-sized. So this will be the Euclidean space, and it's the flattest thing you can think of. The so the Riemannian metric just doesn't change at a point, and geodesics are straight lines. And everybody knows how to write the Riemannian metric in coordinates, in polar coordinates like that. And it will give the following. G, or xp star of G, centered at some p, is equal to the following. So dr squared plus r squared. So yeah, I'm cheating a little bit. But once we will have gone here, we will know what this is. So this is the round metric on Sn minus 1. Okay. So now, Sn. So I already draw it here, but I guess there's geometry in the title, so there's never enough drawing. So this is our standard usual sphere with the great circles as geodesic, and the Riemannian metric is just the metric induced from the usual embedding. Here, so my sphere has radius 1. Here G is equal to dr squared in this coordinate plus sine squared of r g s n minus 1. Okay. Now the hyperbolic space Hn. Okay. So will you talk about it, Sylvain, a little bit? Or H3, H2? No, not that much. Okay. Well, so in the n equal 2 case, it's probably the best way to visualize it. And so it's some metric on the disk where there's a lot of parallel. This is where it's coming from. And geodesics are circles which are orthogonal to the boundary circle. Okay. But here, from a more computational point of view, okay, so I want something which is the opposite of the sine function. That will be the hyperbolic sine. So it has that interpretation. So hyperbolic sine squared of r g of Sn minus 1. Okay. So, okay. So do I need anything else from that? Not yet, I think. Okay, okay. I wrote a set of notes. I think I'll send. So they are still incomplete and with some missing parts, a lot of missing parts actually. But I'll send the Dropbox link to Gérard if you want to read them. But anyway, so let's see. Well, okay. So now let's come at least to one of the parts of the title, curvature. So let us first write some big formulas and then tell you what it's about and why it's important. So, okay. So, what is R? R is the Riemann curvature tensor. Can be seen in the following way. So it's something which eats 4 vectors and gives you a real number, and you compute it that way. So you take dy dx z minus dyx z, and you take the inner product with t. If you've learned it with the opposite convention, ask Gérard. That's him who told me to use this convention in the first place. So, well, that's a huge beast, but should be thought. So Aaron Neighbor presented that way. So if you write it in coordinate, it involves second derivative of the metric. And this is in some sense the right notion of Hessian of the metric. So to define the Hessian of a function, you need 2 directions to say what's going on. Here, you define the Hessian of a bilinear form, so you have 2 more indices. So yeah, that's all it can be. And why do we need this kind of convoluted stuff? So we will see shortly what the Hessian of a function, or actually we could define that for a tensor 2 is. And the Levi-Civita connection is built in such a way that it has 0 covariant derivative and 0 Hessian, so we need something like that if you want to consider derivatives of the metric in some geometric way. So okay, Hessian is nice, Laplacian is good too. So now let's go to the Ricci curvature. So this will be equal to the sum from y equal 1 to n of r ei x. Yeah, there's a lot of symmetry in that thing. Not sure I have the time to. So what is the best definition? Probably the other way around. X ei y ei, where ei is an orthonormal basis of the tangent space. So you can define this at every p if you want of Tp. Okay, so this is the trace of the Hessian, so this will be the Laplacian of the metric. Okay, now let's look at what's going on here. Maybe we will have some tools to compute that, but I won't give you the tools to compute this kind of stuff. Maybe you already know them actually. So what's going on here? So here it's easy. Well, here actually it's pretty easy to compute. The Levi-Civita connection on Rn is just like directional derivative of a vector field seen as a map from Rn to itself. And the fact that like partial derivative commute in Rn will tell you that this here has to be 0, and so that the Ricci curvature also has to be 0. Okay, so yeah, maybe some, apart from this interpretation, so it kind of tell you the curvature measure the lack of commutativity of covariant derivatives acting on vectors but also on other tensor fields. Here, so here I need the vector fields, but well, this is a sectional curvature. I won't need that much, so I won't go into details, but just to give you an idea. So this is if the vectors x and y are orthogonal and have the same norm. So the curvature is equal to 1. And from that, it's not too hard to see that the Ricci curvature, which is a bilinear form, is actually equal to n minus 1 times the metric. Here, hyperbolic space. So, and actually on a formal level, it's really all that's going on. You get some minus sign that comes. So minus 1 constant, minus 1 sectional curvature, and Ricci is equal to minus n minus 1 g. So those 3 examples are the most symmetric examples of Riemannian manifolds. So you can move around, they are homogeneous, but they are also homogeneous acting on the tangent bundle. So they are homogeneous and isotropic. Okay. So,
how does G appear in this formula?
Okay. So here, Ricci it's 2 vectors. So it's a bilinear form. Okay? So what does this mean? That means that Ricci of, so G is the Riemannian metric here. Okay? So that, the Riemannian metric is a bilinear form. So that just means that Ricci of xy, how do I compute that? This is n minus 1 times G of xy. Simply that. That's okay? Okay. Okay. So I guess I'll continue there because I want to pursue that here. So that's it for curvature. Now, so I promised you some calculus. Now is the calculus part. So, well, this will be calculus. So first, first object we will see is the gradient of a smooth function from M to R. So you have learned already a way to differentiate function defined of manifolds, and what this gives you is some du, which is a differential form. So it eats a vector at each point, or and gives you a real number, or it takes some vector field and it gives you a smooth function. So with the metric, so this is the usual business with inner product spaces. You have a duality between the space and its dual. So that definition. So the gradient of U is the only vector field such that well, for any other vector field x, du of x as a smooth function is equal to g of gradient u x. Okay. Now some other operator. Okay, maybe example. So if in these coordinates here, so let u equal the distance from some fixed point P to some other point. So here, by definition, if you are here and you take the image by the exponential map of this line, this will be a minimizing geodesic. So the distance from this point to this point will be the length of this geodesic. And so it will actually be the distance in the tangent space. And what that tells you, if you think a little bit about it, is that the gradient of this distance function, so on, well, m minus p union cut p, so wherever the distance function is smooth, so the gradient of u is actually the push forward of the radial vector field here. Unit radial vector field here. Okay? Okay, so we have du. So we have the gradient. So, well, one of the main players in that game is the Laplacian. So we are one step away from defining a Laplacian. All that we need is a divergence. There are several ways to do that. Yeah? Yes, because u is this function, and so that depends only on p, okay? I could have called that r sub p or something like that. Maybe that would have been a better idea, I don't know. Okay? Okay, so now we need the divergence. But first, we need the following stuff. How to compute volumes on Riemannian manifolds. So I'll assume here M is orientable. So what we need to integrate function, like in the, like talking about like differential geometry class, not measure theory class, is a smooth volume form. And here, so there are a lot of them. You can always multiply that by a positive function that gives you a new volume form. But on a Riemannian manifold, there's a better choice is to ask the volume form, when evaluated on an orthonormal basis, to give 1. So, definition, dVg is the only volume form such that dVg of E1 En is equal to 1 on any orthonormal basis, or frame field actually. Actually, with what we have shown, you can prove the following. So if you take the covariant derivative of the volume form, defined in that way, you get 0. So this is a parallel object. Okay. So now let us define the derivative of a vector field, the divergence of a vector field. If X is a vector field, so the divergence of X is the only function such that so I look at my volume form. I push it along the flow lines of X. That will give me a new volume form, so it will be some function times the original volume form. And this function is the divergence of the vector field. So divergence of X times dVg. Okay, now we can define the Laplacian, and we will compute the Laplacian of the distance function in that cases. So definition. So the Laplacian of u is equal to the divergence of the gradient of u. Okay. So let's see what we can do with that guys, with those guys. Okay. So maybe, yeah, I make 3 columns the same way. I have 3 test cases, so Rn, Sn, and Hn. Okay, so what will be the volume element on Rn? So, well, you need to sit down a little bit and to see how things scale to get something reasonable. But after a while, you'll see that there is only one sensible choice, which is so r to the n minus 1 dr and the volume element on the sphere. So yeah, in R2 you get the usual formula, r dr d theta. Okay, on Sn, dVg will be sine r to the n minus 1 dr dv s n minus 1. And here dVg will be the same with an hyperbolic sign. So sine h r to the n minus 1 dr dv sn minus 1. Okay. So now let us compute the Hessian of the distance function. So, well, yeah, will I call it R or u? Okay. So let us assume that u is the distance from P, the center of where I defined my exponential chart, to some moving point. So P is fixed. The second argument here is my variable. So I want to compute the divergence of the gradient of u. So gradient of u is equal. Well, everything we do is coordinate independent, so we can compute that here, or more precisely here. So gradient u in that exponential coordinate chart is just this radial vector field. So now let us differentiate the volume form. L dr of dvg. So this will satisfy a Leibniz rule. But so if we push that along the flow lines, if we push this form along the flow lines of this vector field, nothing changes. And here, nothing changes too. So only that guy gets differentiated. So this will be dr sine r to the n minus 1, and then dr dv s n minus 1. Okay? So then I want to write it as some function times my volume element, which I wrote here. So this will be dr of that guy. Times dvg. Okay. So there's actually, yeah, when you do the computation, it's actually not too hard. So, and this gives you n minus 1 cosine r over sine r dvg. Okay? Yes. So here, so this guy here, this function, this is the Laplacian of my distance function. Using the exact same procedure here, we get the following. So here, Laplace u with the same u is n minus 1 over r. And here, Laplace u is hyperbolic cosine r, n minus 1. N minus 1 hyperbolic cosine of r over hyperbolic sine of r. Okay. What else do I need? Okay. Do I have 5 minutes or 35 minutes left? C'est jusqu'à 5 heures. Oh, okay, perfect. So, okay. So, well, what do you want to do with these guys? Well, basically integration by parts, Stokes theorem. Everything works the way you want, and in particular, you can do the following thing. So, maybe let me write the most, maybe not the most useful. But well, maybe something which summarizes everything. So this will be equal to, so theorem is compact boundaryless. So there are also version version of that theorem on manifold with boundary, but I guess we will see them when we need them. So you can do integration by parts. Well, that's wonderful. Okay, so we did some calculus. Yeah. Remark. Maybe this is not the definition you have worked with so far. I don't know. No, this remark will come later. Now let's think about the Hessian. One last remark. So what does the Laplacian of the distance function tells us? Well, it tells us, so what are the, so we have seen that the gradient is this radial vector field in the tangent space when you look at an exponential chart. So the geodesics here are just straight lines, and the integral field of this vector field, the integral lines of this vector field in this chart are geodesic for the metric. So with this formula, the Laplacian tells us how, when you move along geodesics, when it's the Laplacian of the distance function, so when you move along geodesics, how fast is the volume measure changing? So that tells you that. Now, let us look at the Hessian. So here, so we will come back to that later. Okay, so there are several, at least 3 definitions of the Hessian, and each has, oh, I said I'd use D for the Levi-Civita connection. That's bad. I managed to do that in my notes, but on the blackboard I have trouble. Okay, so first, so df is a one form. We have seen how to compute covariant derivatives of one form. So they are actually tensorial in the direction in which you differentiate. So that will give you a 2 form. So df is the Hessian of the function f. Okay, that's a definition. Takes 2 vectors, gives you a real number. That's fair enough. Exercise, which is just a little exercise in computing with covariant derivatives. ddf is symmetric. So yeah, that looks good for a Hessian. Second definition. Maybe, okay, yeah, I guess I'll hide that. So what, is what's on top still relevant? No, okay. Okay, so this is a symmetric bilinear tensor. Whoops. Come back. Sorry. Oh yeah, that's perfect. So once again, another definition. For the Hessian this time. Okay. That will probably look a bit strange at first sight if you haven't encountered that. So the Hessian of f is equal to 1/2 the Lie derivative in the direction of the gradient of f of the metric. Okay? So that's so the Hessian, so exercise. Maybe I could do that actually. Yeah. Let us prove that. Okay, so let us pick some vector field xy. So, and let us compute that. Well, I just compute that. So, nabla f of g evaluated on x and y. Yeah, one point. With this, it's automatic that it's symmetric. It's the Lie derivative of a symmetric tensor. It's still a symmetric tensor. Okay, but for those who are not familiar with that kind of computation, so I use Leibniz rule once more for the Lie derivative. Okay, so that's a first step. And then I need to subtract the Lie derivative of both of those guys. So that will give me Lie brackets. G nabla f x y minus g of x nabla f y. Okay. So that's not too bad. Okay, now I will once again use Leibniz rule, but for the covariant derivative here. So when I differentiate that, I can take the covariant derivative of both of these vector fields. So here I'm writing the first line. X. Okay. Plus g of x d gradient f y. And here I will, so there's a link between Lie bracket and connection. So yeah, some of you are nodding. I guess that's a computation we've maybe all made, but it's a computation that works well. So. Dx nabla f y minus g of x d nabla f y minus dy nabla f. Okay, so some cancellations. Good. So that guy, well, that whole guy actually goes away with this one. That whole guy goes away with this guy. So in the end, what we get is g of dx gradient f y. Okay. Plus g of dy gradient f. Oh, x dy gradient f. Okay. And now, so, okay. Well, yeah, I said I'll prove it, I'll prove it. So, so this is a third possible definition of the Hessian. This is not the one I chose. So x times g gradient f y, okay? So minus g gradient f dx y, okay? Plus y y times what? G of x still? Yeah, gradient f plus g of minus, sorry, g of dy x gradient f. Okay, so this is x dot so this is df of y by definition of the gradient. This is df of dxy, and similarly. So what we get here is almost, well, actually the definition of the second derivative, of the covariant derivative of the function df. So that's ddf of xy, and the second will give you ddf of yx. But I told you it was symmetric. So that's 2 ddf of xy. And we're done. Okay. Okay, so that's another interpretation. So let's look at what that gives us in a normal chart through the exponential map. So recall that so I work once again with an exponential chart. Okay. So the pullback of the metric, as I said, is of the form dr squared plus some metric on the sphere inside the tangent space. So let us once again take u to be the distance from P. And let's look at the Hessian of u. So Hessian of u is equal to, let's take this stuff. So 1/2 Lie derivative in the direction of gradient u of g, but g is that guy, dr squared plus hr. Okay? So 1/2. Here, well, basically this vector field is a coordinate vector field inside the exponential chart. So dr squared plus hr. And if you take, so this derivative doesn't change at all when you move along this radial direction. So you will see only this guy. 1/2 L dr of hr. So what that tells you? That tells you that the Hessian of the distance function, and we will see that it's really important to control that, controls how this part of the metric, how fast it is changing when you start from the center of the coordinate chart and move along. And actually, so with this kind of stuff, we will see that when we have function whose Hessian have special property, is actually some function times the metric, then we get a lot of rigidity. Okay. So okay, so maybe let me just state a formula that will be the core, the main tool of the whole business. I think I have defined all the elements to state it. So a proposition, and I'll maybe leave that as an exercise. So let f be any smooth function then, okay, what does it tell you? Take 1/2 of the Laplacian of gradient f squared. So this is a smooth function. I can take its Laplacian. This is equal, so gradient of the Laplacian inner product with gradient f plus norm squared of the Hessian of f plus a curvature term. So this is called Bochner's formula. And this will actually be the most complicated tensor computation we will use. There's nothing, we need nothing more. Can get a lot of mileage out of that. So yeah, what is it useful for? So maybe let's look once again at the distance function. So we've seen the gradient of the distance function is dr. So this is a unit norm vector. So let's apply this with f, the distance function. So outside of the cut locus, this guy is always 1, so that will give 0. This will be the rate of change of the volume element here. So this will be some control on the rate of change of this part of the metric. And we see that if we have information on the Ricci curvature, that can tell us some stuff about what's going on here. Okay? So that's why, and actually all the theorem I know that we will see in comparison geometry rest on this formula. So for the distance function, we can do that. Assume we have a harmonic function and that the Ricci curvature is non-negative. Then we get that the gradient is subharmonic. Its Laplacian is greater than 0, which is really useful for a lot of applications. And yeah, maybe I'll resume with that tomorrow. So starting with that, we can also assume f is an eigenfunction of the Laplacian, and you can get really nice results, and I guess I'll start with that next time. Thank you.